Hi and welcome to the session. In this session, we are going to discuss about the topic principle of infrared spectroscopy, conditions to absorb infrared radiation and modes of vibration from unit 5, that is spectroscopic technique, and the part IR spectroscopy. In the last sessions, we have discussed about the electromagnetic radiation and interaction between the electromagnetic radiation and the matter, and based on these interaction different analytical methods has been designed, and these analytical methods are the spectroscopic methods of analysis or spectroscopic techniques. So here we are going to discuss about the IR spectroscopy. As we know that in IR spectroscopy, infrared radiations are used to analyze the analyzed sample. This is a kind of absorption spectroscopy, and the infrared radiations is absorbed by the analyzed sample, and based on this absorption nature of the analyzed sample, the analytical parameter will be obtained for a specific analyzed sample. So we will see the principle behind the IR spectroscopy. We know that a covalent bond which is between two atoms is always in a oscillating state. It is acting just like a spring, and it is always in the vibrating state. Now this oscillating state leads to the change in the dipole moment in some molecules. This change in dipole moment in certain molecules due to the oscillation of the covalent bond generates a varying electromagnetic field. The intensity of this electromagnetic field depends on the variation in dipole generated by the or induced by the vibrating molecule. Greater the change in the dipole moment, larger will be the intensity produced by the electromagnetic field. That means higher the change in dipole, higher intensity of the electromagnetic field will be obtained, which is produced by the vibrating molecule. Now you can see this, a molecule which is always in vibrating state. The covalent bond is acting like a spring. In that case, it produces a electromagnetic field. It will produce a electromagnetic field, and the electromagnetic field which is produced is having intensity depending on the change in dipole moment made by this vibrating molecule. When such vibrating molecule is bombarded or irradiated by infrared radiations, in that case the infrared radiations which is having frequency equal to the frequency of electromagnetic field produced by the vibrating dipole, then only the IR radiation will get absorbed by that vibrating molecule. In simple way, when the frequency of the electromagnetic field produced by the vibrating dipole is equals to the frequency of IR radiation which is allowed to fall on that molecule, then the molecule will absorb that IR radiations because both are having equal frequency. So simply only the infrared radiation having frequency equal to frequency of electromagnetic field produced by the vibrating dipole will get absorbed. Now the resultant electromagnetic field oscillate with the double amplitude to that of electromagnetic field produced by the oscillating dipole. If the vibrating molecule does not change the dipole, then IR radiation will not absorb in that case. That means only the molecular vibration that leads to change in dipole is having ability to absorb the radiation, IR radiation. So this carbon dioxide molecule can vibrate by four ways. First is the symmetric stretching, second is the asymmetric stretching, third is the bending in the plane, and fourth one is the bending out of plane. Now if you see these four vibrational state of carbon dioxide, then in that case the first, that is the symmetric stretching, will not lead to the change in dipole, while asymmetric stretching will lead to the change in dipole. Here bending in plane and bending out of plane will be also changing the dipole during the vibrations, and hence the symmetric stretching in case of carbon dioxide molecule is IR inactive in nature. That means only the molecule which is changing the dipole during the vibration of the bond will be able to absorb the IR radiation, while if it is not changing the dipole during the vibration, then such kind of molecule will be IR inactive in nature, or the vibrations will be IR inactive in nature. The second condition to absorb IR radiation is only the IR radiation having frequency equal to frequency of electromagnetic field produced by oscillating dipole will be absorbed. So these are the conditions to absorb the IR radiation. So first condition to absorb the IR radiation is what? First of all, the vibration in a molecule should change the dipole moment. Second, the IR radiation frequency should match with the frequency of electromagnetic radiation produced by the oscillating dipole. Then only IR radiations will get absorbed. Now here the intensity of the absorption, that means intensity of the infrared radiation absorbed by that molecule, depends on how efficiently the energy of IR radiation is transferred to the vibrating atoms. Ultimately, the intensity of absorption depends on the change in dipole due to vibration. Higher the change in dipole due to vibrating bond, higher will be the intensity of absorption for IR radiation. Now, if I ask one question, that give the examples of the molecule that do not absorb IR radiations, then what will be the answer from you? The answer will be, in this case, the molecule like H2, the molecule like O2, the molecule like N2 are IR inactive in nature. They do not absorb the IR radiation. Now again the second question arises, why these molecules are not having IR activity, or why these molecules do not absorb the IR radiation? Now if you see the vibrational state of these molecules, so you can see H2, O2 and N2. Now if you see the vibrational state, there is only one vibrational state is there in this molecule, and that vibrational state is nothing but the symmetrical stretching. So due to the symmetry in this molecule, there is no change in dipole moment due to the vibration, and hence they are IR inactive in nature. They do not absorb the IR radiation. Now we will discuss about modes of vibration, how to calculate the number of modes of vibration for a molecule. Now modes of vibration is the evaluation of how many ways a covalent bonded molecule can vibrate. For a linear molecule, modes of vibration can be calculated by using formula 3n minus 5, where N is the number of atoms in a molecule. For a non-linear molecule, modes of vibrations can be calculated by using formula 3n minus 6. Here, n is the number of atoms in a molecule. Further, the theoretical number obtained for the modes of vibrations may not be always equal to actual analytical evaluation. That means if you calculate the modes of vibration, that may not be always equal to the actual peaks obtained in the IR spectra, IR graph, and that may be due to the symmetry in the molecule. That means there is no change in dipole in that vibrational state. Second, the vibrational energy may be the same. Third, the intensity of the peak may be very low. And fourth, the vibrational energy may be beyond the range of IR spectrum. Now again, the theoretical number obtained for the modes of vibration may not be always equal to actual analytical evaluation because it may be due to symmetry in a molecule which will lead to no change in dipole. Second, energies of the vibration are identical. That means both the vibrational state will absorb the IA radiation of same wave number. Absorption of the intensity is too low. And fourth one, the frequency beyond range of instrument. For example, for CO2 molecule, the calculated modes of vibration are 4. But actually, only 2 will be absorbed after IR analysis. So we'll see that this is the infrared spectra of carbon dioxide, and you can see that there are 2 peaks obtained in a spectra, and this spectra has been taken from this website which is given at the bottom. Now, why there is only 2 peaks in the spectra, but by calculation it is showing that there are 4 modes of vibration in a carbon dioxide. Now you can see that in carbon dioxide there are 4 modes of vibration, possible modes of vibration. First is the asymmetric stretching, second is the symmetric stretching, third one is the vertical bending, that may be called as a bending in plane, and fourth is the horizontal bending, that may be also called as a bending out of plane. Now if you can see that the symmetric stretching is IR inactive because there is no change in the dipole, so the 1 out of 4 will get cancelled. Again, the vertical bending and horizontal bending both will have same energy of absorption. That means both the vibrations will absorb the IR radiation of same wave number. So because of that, only 2 peaks will be obtained. If you can see from the left hand side, the peak A is due to the asymmetric stretching, while there is a absence of the peak due to the symmetric stretching because it is not changing the dipole. Further, there is another peak in the graph which is due to the vertical bending and horizontal bending, and both are having same energy of absorption, and hence only 2 peaks will be observed in a IR spectrum due to the symmetry and same energy of vibration in a molecule. Now further we will see the calculation of modes of vibration for diatomic and polyatomic molecule. So here first we'll take HCl. Here N will be 2, so molecule is the linear, and hence the modes of vibration will be calculated by using formula 3n minus 5. So here 3 into 2 minus 5, that will give us 1. So HCl will show only 1 mode of vibration. Second molecule is H2O. H2 is a non-linear molecule, hence the modes of vibration will be calculated by using formula 3n minus 6. So 3 into 3, where n is the 3, that is the number of atoms in a molecule. So 3 into 3 minus 6, that will give us 3 modes of vibration. Then ammonia, NH3, again here 4 atoms are there in a molecule. So 3n minus 6, here n is 4, so 3 into 4 minus 6, that is equals to 6. So here 6 modes of vibration. Then methane, 5 atoms in a molecule, so here it is non-linear in nature, so 3n minus 6, 3 into 5 minus 6, that is equals to 9. Ethane, 3n minus 6, as it is non-linear, here the number of atoms is equal to 8, so 3 into 8 minus 6, 18 modes of vibration. Then benzene, C6H6, 12 atoms in a molecule, so 3 into 12 minus 6 is equals to 30. And finally NO, so 2 atoms in a molecule, which is a linear molecule, so 3n minus 5 is equals to 3 into 2 minus 5, that is equals to only 1 mode of vibration. So in this way we can calculate the modes of vibrations for diatomic or polyatomic molecule. So finally, in summary, we have studied in this session what is the principle of IR spectroscopy. So here, in case of principle of IR spectroscopy, the vibrating molecule which shows change in dipole moment during the vibration produces the electromagnetic field, and if this molecule is irradiated with the infrared radiation, then if the frequency of the oscillating electromagnetic field matches with the frequency of IR radiation, such IR radiations will be absorbed by the molecule and the final electromagnetic field will have twice amplitude to that of original one. That is the principle of IR spectroscopy. Then what are the conditions to absorb IR radiations? There are two conditions to absorb IR radiation. First is the oscillation of a molecule should show change in dipole, and second one, the frequency of the IR radiation should match with the frequency of oscillating electromagnetic field produced by the vibrating molecule. Then efficiency of absorption for IR radiation. Higher the change in dipole due to the oscillation of a molecule, higher will be the absorption of IR radiation. How to calculate the modes of vibration? So we have discussed about how to calculate the modes of vibration. For a linear molecule, the formula is 3n minus 5, where n is the number of atoms. For non-linear molecule, the formula is 3n minus 6, where n is the number of atoms in a molecule. Further, we have discussed about why the actual and theoretical modes of vibrations are differing. So here in this case there are 4 reasons. First is due to the symmetry in the vibration or in the molecule. Second is the energy of vibrations may be equal. Third is the low intensity of absorption, and fourth one is the energy of absorption may be out of range. So in this session we have discussed all these points. In the next session we will discuss about the components of IR spectrophotometer and working of IR spectrophotometer. Thank you.